Have you ever wished batteries to be lighter and with a higher energy density? But what if a new battery design leads to fire and explosion? To create safe new energy storage technologies, defects such as dendrites in lithium metal batteries must be detected and mitigated. That's what I do. I help material scientists to detect battery defects by transforming 3D images into information. My task is to detect defects such as dendrites, which can occur both in the standard batteries, named lithium-ion, as well as in the more advanced lithium metal batteries. I'm Daniela Ushizima, and it's my pleasure to share with you our last updates on lithium metal battery characterization using X-ray imaging and machine learning methods. So let's get started. So let me summarize what this presentation is all about. First, you see a set of slides that will give you the context, where the samples come from, which instrument is used to acquire the data, and how to recognize relevant events from that data. Next, we'll discuss what material scientists do to test batteries and what the battery defects look like. Then let's frame the problem as a machine vision task. Then we can show semantic simulation results using different machine learning approaches. Next, we will introduce a new convolutional neural network, followed by modeling dendrites and simulating their growth using phase field methods. And finally, our team and future challenges. So where the samples come from? They come from the National Fuel Cell Research Center, which is located at the University of California, Irvine. It's a center that results from a partnership between the U.S. Department of Energy and the California Energy Commission. This center aims to facilitate and accelerate the development and deployment of new energy storage technologies. The Associate Director, Iryna Zenyuk, is a key member of our team. Her team, they provide expertise on lithium metal batteries, including the samples. So let's get to the samples. Our team also counts with the collaboration of a beamline scientists from Berkeley Lab, Advanced Light Source, or ALS, who are responsible for imaging the samples and providing reconstructed data that enable to visualize the morphologies of interest. In addition, the research work that I'll present today also leverages some of the algorithms that we developed to inspect other imaging modalities, as those that I show here. By interacting with domain scientists, my team and I have used prior information, I'm calling here physics aware, to provide a set of measurements about the observables. And all of this to say, we've worked with images for several kinds of samples before, and now some of these knowledge is applied to lithium metal battery. The problem. One of the problems of rechargeable batteries is explosion. Of course, this video shows an extreme case of battery damage. But why does it explode? If you answer degradation of the separator, you're right. Next slide, I will show some images of electrochemical modifications of batteries that can lead to explosions, as dangerous as when piercing a battery with a knife. Lithium metal batteries, or LMBs. These are electrical batteries that can use solid electrolytes to provide a more stable interface with lithium metal. These lithium metal solid state batteries have shown potential of delivering superior electrochemical performance. This means increased charge storage capacity and the ability to hold almost twice the energy of a traditional lithium-ion. In other words, higher energy density at lower battery weight and size. But before manufacturing a new LNB, one battery task consists in quantifying the deposition of lithium during battery charge. If the deposits form spiky clusters, we have dendrites. And if they grow, as illustrated in the diagram, they can pierce the separator and lead to a short circuit and possibly an explosion. While the diagram explains the dangers of dendrites, it does not represent the exact design of our batteries. Instead, We use lithium symmetric cells with a polymer electrolyte membrane. The images on the real data, yes, those correspond to microtomography slices of our batteries. How to see inside these batteries? Most of the images we will see today come from beamline 832 end station, which has a new sample rotation stage, a new sample elevation stage, and a new lens system. Later improvements allow experiments to achieve sub-second time resolution scanning. Scans generate sinograms. On the right, we show the reconstruction procedure that transforms sinograms into a stack of image slices. There are several reconstruction algorithms we are investigating, particularly considering sample deformation. Today, I'll show reconstructed stacks using only TomoPy with a grid rack. The result of data reconstruction is microtomography images, or micro-CT for short. Here you see 4 examples of reconstructed data from lithium symmetric cells sealed in an aluminum foil pouch, similar to the picture on the left. Quality control. So which are the factors that control the formation of these defects? Understanding how dendrites form and grow is key for safer designs and preventing any short circuit. That's why we use tomography data to look inside batteries during charge-discharge cycles. But looking is not enough. Taking pictures is just the start. Quality control and quality assessment requires quantifiable metrics. This means detecting and measuring dendrites automatically. That's what we do. We create deep learning algorithms to automate inspection of battery data acquired with advanced instruments at DOE national laboratories, such as Berkeley Lab ALS and Argonne National Laboratory APS. By using X-ray tomography as the input data, as well as prototypes defined by our battery experts, we detect battery defects and measure their growth during cycling. Next slides. We'll show how these defects, such as dendrite and pitting, are detected. Preliminary results. Let's get to the details of our algorithms implemented in Python that detected dendrites in pitting from micro-CT of batteries. Here I will discuss choices of algorithms and show corresponding results of a semantic segmentation. Multi-layer perceptron, or MLP. One of the first neural networks we used was an MLP, represented by the network in figure B, where each node is a perceptron, as in figure A. The MLP combines several perceptrons, and the number of hidden layers is often referred as the depth of the neural network. So let's take a look at some of the results. So here's the result of running MLP as part of a routine to detect if a certain stack has or not patterns that look like dendrites. This work was performed using maximum intensity projections as input and MLP configurations as I show on the right. In addition to MLP, we have also explored convolution neural networks, or CNN. Let's take a quick look at some of their differences and similarities. MLP, fully connected layers. CNN, partially connected convolutional layers. Here comes the concept of local information is more relevant than information afar. YNet. This newly proposed segmentation network called YNet is different from the broadly used CNN called UNet, which has 2 parts, encoder and decoder. The YNet has 3 parts. First, a regular convolutional module shown in blue, which constitutes the left branch. A pyramid pooling module shown in brown, along a dilated convolution module shown in orange, which after concatenation and convolution constitute the right branch. The result feature maps from the right branch are then added to the output of the regular convolution module, which allows for the correction of the features that would have been missed by either branch. In other words, the output of each branch constitutes a residual correction for the other, thereby refining the result at each node as represented in white boxes at the center. The nodes are then upsampled and concatenated with transposed convolution feature maps shown in red and yellow of the corresponding dimension. Throughout the network, We use ReLU as a nonlinearity after each layer and add L2 regularization to account for possible overfitting scenarios that could have occurred during training. These are some of the preliminary results obtained using YNet. We also give here on the right the information on how we split the data sets into training, validation, and test, and also compare the results with UNet and YNet with respect to the detection of dendrites and pitting. In addition, we have also studied phase field methods as mathematical tool for describing interfaces and their motion. This method was originally developed as a model of solidification, which enabled us to simulate complicated structures like dendrite crystals. And this work is only possible with the collaboration of several people. So this slide summarizes our efforts and the scientists involved in this work. Together, this team has created a new set of machine vision machine learning algorithms based on convolutional neural networks focused on three-dimensional X-ray data of solid-state batteries using a polymer electrolyte membrane, which was provided as a research sample by ionic materials. Only by identifying L and B defects and tracking them during battery cycling, we can monitor the lifespan of a battery and the evolution of dendrites. In conclusion, this is ongoing work, and next steps will include exploring other segmentation methods, dendrite tracking, and space-time correlation among different types of defects. If you would like to hunt for hidden patterns within battery data and accelerate energy innovation, contact us. I'm Daniela Ushizima, member of CAMERA, and I lead the machine vision research team behind this investigation. Thanks for listening.